Reinforcement learning is difficult for beginners. A major reason is that reinforcement learning has numerous terminologies. Beginners can be overwhelmed by those terminologies. But you have to understand and remember all the terminologies. There's no way around. In this lecture, let's study the terminologies one by one. The most important concepts are state and action. For example, when you play the Super Mario game, you can think of the screenshot as state. Admittedly, this is not rigorous. Such a screenshot is typically called observation. But deep reinforcement learning people oftentimes do not distinguish between state and observation. When you play the Super Mario game, you observe the current state on the screen, and you will react accordingly. You can manipulate Mario to perform different actions. For simplicity, let's assume Mario can choose from only 3 actions. Go left, right, or up. Left, right, and up are called actions. In this example, Mario is called agent because it performs actions. In the case of self-driving car, cars are agents. In the case of robotics, robots are agents. In sum, in an application, the one who performs actions is called agent. The next concept, policy function pi. What does policy mean? Policy means making a decision based on the current state. When you play the game, you observe the state on the screen. Then how will you control Mario? Will you let Mario move left, right, or up? Probably moving up, because Mario can avoid enemies and collect coins. The policy in your mind is to avoid enemies and to collect coins. Formally speaking, policy function pi is defined in this way. Pi maps the state-action pair to a probability score between 0 and 1. Pi is a conditional probability density function. Pi of A given S is the probability of taking action small a when observing state small s. For example, when observing the screen, the agent can make one of the 3 actions, left, right, or up. Feed this image to policy function pi. Pi will output 3 probability scores. The probability of moving left is 0.2. The probability of moving right is 0.1. The probability of moving up is 0.7. The probabilities output by the policy function will guide the agent to make decisions. With the probabilities at hand, let's perform random sampling. All of the 3 actions may be chosen, but moving up has the highest probability, 0.7. Moving left and right are also possible, but their probabilities are lower. Decisions are made by the policy function. The policy function tells the agent what to do. How to learn the policy function is the main theme in reinforcement learning. In this example, the agent's actions are random. Actions are sampled from the probabilities computed by the policy function. Different from the random policy functions discussed here, a family of policy functions makes deterministic decisions. Given the current state, the action is non-random. In the Super Mario game, both random policy and deterministic policy will work. However, in some applications, making random decisions is necessary. For example, when you play rock, paper, scissors with another person, you must use random policy. Otherwise, if your policy is deterministic, your opponent will find your pattern and can predict your next action. In this way, your opponent will beat you based on your pattern. You have a chance to win only if your policy is random. Another terminology, reward. After Mario executes an action, the game will provide Mario with a reward. How to define the reward is up to us, and it is crucial to the outcome of reinforcement learning. For example, I can define the reward in this way. When Mario collects a coin, it receives a reward of positive 1. The reward for winning the game should be set very big. For example, when Mario wins the game, the reward is 10,000. If Mario unfortunately touches the enemy Goomba, Mario will die and game over. Let the reward be negative 10,000. So Mario has a motivation to avoid enemies. If nothing happens, the reward is 0. The goal of reinforcement learning is to maximize the cumulative reward. The way we define the reward will affect the learned policy. For example, if the reward for winning the game is not big enough, then Mario will try his best to collect coins rather than winning the game. Another terminology, state transition. Given the current state, Mario executes an action. Then the game will generate a new state. This is known as state transition. For example, if Mario moves upward, then the next frame on the screen will be different. This means the state changes. The action executed by the agent leads to a new state. State transition can be either deterministic or random. We typically assume the state transition is random. The randomness is easy to understand if you know the Markov chain. The randomness in state transition is from the environment. What does environment mean? In this example, the environment is the game. The program of the game determines the next state. In robotics applications, robots are the agents, and our physical world is the environment. In recommender system applications, the websites are the agents, and the customers are the environments. State transition can be random. The randomness in state transition can be understood in this way. When I control Mario to jump, it will move to the target position. Mario's next position is determined by the action. This part is non-random. However, the enemy Goomba may move left and may move right. Goomba's movement is random, and it is determined by the environment. I have no control over Goomba's next position. Because of Goomba's randomness, the next state is random. The randomness is from the environment, namely the game program. We denote state transition by function p of s prime given s and a. P is a conditional probability density function. S is the current state, A is the current action, and S prime is the next state. Given the current state S and the current action A, the P function outputs the probability of the new state S prime. In our example, the next state will be that Mario moves upward, but Goomba's location will be random. It will be left with probability 0.8. It will be right with probability 0.2. In practice, we don't know the state transition function P. We know there is a state transition function, but we don't have this function. Only the environment has the function.